Figure 13.25, Case Study, Payroll System Using Polymorphism and Runtime Type Information with Dynamic Cast, Type ID, and Type Info. Now, you may recall in the original problem statement for this employee class hierarchy that we said that the company wants to give base plus commission employees a 10% base salary raise for this pay period. And we haven't implemented that part of the example yet. So here we're going to take a look at a new version of the main program in which we're going to demonstrate how in a polymorphic system you can do type-specific processing. Remember, when you're invoking virtual functions via a base class pointer or reference, you can only call base class member functions via the base class pointer or reference. So in order to change the base salary for a base salary a base plus commission employee, I need access to the set base salary member function, which I can only have via a pointer or reference of type base plus commission employee in this example. So let's take a look at what we're going to do in this version of the program. Here we're starting right away with a vector of 4 employee pointers. And for the purpose of this example, we've decided to dynamically allocate each of the employees and immediately take the pointer that's returned by new and place it right into the employees array. Now remember, when I say new salaried employee, I'm going to get back a pointer of type salaried employee that is aimed at the memory that was just allocated and initialized. And because it's a pointer of type salaried employee, and a salaried employee is an employee, I can assign it to employees sub 0, which is an employee pointer based on the vector declaration. And we do the same thing here at lines 36 through 41 for our other 3 objects once again. Now, what we want to do is our payroll calculation, but this time we want to account for the base salary increase for the base plus commission employee. So here at lines 44 through 66, we have a for loop that's going to iterate through the employees vector one element at a time. And as we enter the loop, the first thing we say at line 46 is go to the current element that we're looking at and tell that object to print itself. Now again, the compiler looks at this expression and it says what is the type of the thing on the left hand side of the arrow, and one element of our vector is an employee pointer, so it knows that the expression is an employee pointer, and then we have the arrow operator which says dereference that pointer to get to the actual object and then call that object's print function. So again, when the compiler looks at this, it goes to the employee class to see if there's a print function with no arguments, because it doesn't know what type of object this pointer is going to point to at runtime. Now, after having printed the current employee, at lines 50 through 52, we use a new operator that we haven't discussed before. It's used specifically in the context of polymorphic processing. It's the so-called dynamic cast operator, and it's used to perform what we call downcasting. Downcasting is where you take a base class pointer, which is for a type at the top of the hierarchy, and you cast it down the hierarchy to one of the derived class types. So you can see here that we've declared a pointer of type base plus commission employee called derived pointer, and we're assigning it the result of this highlighted expression. And I split this across 2 lines just because in our book we don't have enough width to accommodate this line of code, but just for readability right now, I'm going to put it all on 1 line. And what you can see here is the dynamic cast keyword followed by a set of angle brackets in which we specify the type to which we would like to cast the argument in parentheses. So we want to take that thing in parentheses and turn it into type base plus commission employee pointer. Well, the thing in parentheses is an employee pointer. So the first thing we have to do is make sure that these are related by a hierarchy. If they're not, this cast operation is not going to work no matter what. Now, what happens at runtime is the compiler determines, at execution time, the compiler is not involved. At execution time, what happens is it determines the type of this object, and if the type of this object, number 1, is related by inheritance, and number 2, is specifically a base plus commission employee, then I can take the pointer that's stored here and convert it to this type. So if employee sub I refers to a salaried employee or an hourly employee or a commission employee, this cast operation is actually going to return a null pointer if by any chance the pointer that is stored in employee sub I specifically points to a base plus commission employee object, in that case only will a proper pointer address be returned and assigned to derived PTR. So if this is successful in assigning a non-zero value to derived PTR, then we know that the current element is aimed at a base plus commission employee object, or in a more robust hierarchy, possibly a subtype of base plus commission employee as well. So we then test at line 55 to see if the cast operation worked. If derived pointer is not equal to 0, the cast operation worked. If it is equal to 0, it means that we're not dealing with a base plus commission employee at the moment, and we would skip this if statement and simply display the earnings for whatever employee we are dealing with. Now, in the case of a base plus commission employee, this pointer will be non-zero, at which point we will grab the old base salary by calling derived pointer arrow get base salary. Now, this is allowed because derived pointer is a base plus commission employee pointer, and base plus commission employee contains a get base salary member function. But on the other hand, had I said instead employees sub I arrow, and then I try to access get base salary, you can see just by looking in the list that there is no get base salary for an employee to call. So the reason that we've done this downcast is because we want to do some type specific processing, and the only way to do that is by first taking the current base class pointer and casting it down to one of the derived class types, where you can then access that type's type specific functionality. So we get the old base salary, then we display what the old base salary was. We then set the base salary to 1.1 times the old base salary, which gives us the 10% raise. And then we display for you what the new salary is after the 10% increase. And finally, at line 64 here, we display the earnings. And because this line comes after this if statement, if it happens to be a base plus commission employee that we're currently processing, then by the time we get to line 64, the base salary increase will have already been applied, so my earnings calculation will include the 10% base salary raise. Now I'm going to stop there, even though there's more to this program, and just show you this part of the program's output that's produced by this loop. And just demonstrate to you here. So for our salaried employee, we see the standard salary. For our hourly employee, we see that there's an hourly wage of 16.75 and worked 40 hours precisely, so that's a total earnings of $670. For the commission employee, we had $10,000 in sales and a commission rate of 6% for $600 earned. And then for the base salary commission employee, you can see that first we output all of the information for our commission employee, and you see the original base salary. Then you see the old base salary, the new base salary with the 10% increase, and then the earnings calculation. So the base salary after the 10% increase is $330, and then when you multiply 4% times 5,000, that's another $200 for a total of $530. So as you can see here, we were able to do our polymorphic processing, but in the midst of that polymorphic loop that doesn't really care about what type of employee we're processing, it just prints each employee and calculates its earnings. But in the middle of that loop, we had that type-specific chunk of code that enabled us to do some custom processing, if you will, for base plus commission employee objects. Now, let's take a look at the end of this program, because there is another new feature that I want to show you here. As I mentioned, every object actually can know its own type at execution time. And what I'd like to do is show you that you can access that type and display, in this case, the name of that type. So we have this little for loop at the end of our program where we'll be deleting each of the dynamically allocated objects in our employees vector. And you'll see here this interesting expression in line 72. And basically, we're taking advantage of the type ID operator here. The type ID operator, you give it as an argument an object that is whatever type you want, and it will give you back an instance of a class called type_info, which represents type information for that object, such as what is its class name. And the type_info class has a member function called name, which we're calling on the return value of this expression. So this highlighted part, we give it the dereferenced employee subj pointer, which gives us a specific employee object, either a salaried employee, an hourly employee, a commission employee, or a base plus commission employee. Type ID gives us back a type_info object containing information about that object's type. And when you say .name on that type_info object, it tells you the name of the actual class for that employee object. So if you go and take a look at the output window here, you know from the output up above, let's just stretch this out here, you know from the output that we had a salaried employee, an hourly employee, a commission employee, and a base plus commission employee. And you can see as we loop our way through the vector that we're deleting the salaried employee, the hourly employee, the commission employee, and the base plus commission employee in the same order that they were processed up above. And of course, we're looping through them in the same order here as well. So every single object in C++ actually can know its own type at runtime. It's called runtime type information. And one thing to be aware of, by the way, is depending on your compiler, you may need to explicitly enable that capability before it will work at runtime. So if you get compilation errors, or if you don't get the same output that we showed you in this example when you run it on your own compiler, then what you want to do is check out your compiler's documentation and see how to enable runtime type information. It's usually just a simple flag that you specify at the command line when you execute your compiler, or via a dialog if you're in an IDE like Visual Studio, where you specify that flag, and then from that point forward, when you compile your programs, they will be enabled for runtime type information.